So this is a nice way to think about it because it's hard to imagine 4.6 billion years and keep that in head. But if you set 4.6 billion years as 365 days, then on January 1, okay, the Earth formed. On March 4th, big gap there, right? Earliest life forms, 3.8 billion years. November 9th, first good record of invertebrates. That's animals without backbones, like clams and things like that. November 20th is the oldest animals with backbones, vertebrates, so that's 500 million years ago. We're running out of time, we're already in November. December 3rd, the first vertebrates move on to land. All that before was in the water. December 16th, we're really running out of time here, aren't we? We're now just getting the first mammals, 225 million years ago. The first primates, approximately 66 million years ago. And when do humans show up? Just in time for the party, 11:37 p.m. on New Year's Eve. So we've only been around for about 300,000 years, and we've already trashed the planet, which is really too bad. Or we're busy doing that, I guess. But at any rate, the saber-tooth would be somewhere between the closer to the primate. The first saber-tooth would be about 40 million years. Okay, so here's my outline. We're going to talk about what are saber-tooth cats, when and where did they exist, how do they differ from non-saber-tooth cats, what and how did they kill, and were they social or were they solitary, which is a tough question to answer in the fossil record. So, one of the most important messages I want you to get from all this is that saber-toothed cats are not freaks. I mean, we look at it and we think, oh, how could anything exist like that? That's a cast of a skull from the tar pits over there. But really, they were a highly successful design, and they were the typical big cat everywhere on the globe for most of the past 40 million years. So wherever you would have gone, except say Antarctica or Australia, you would have encountered, as the big cat on the landscape, one or more saber-toothed cats. And they come from a whole variety of groups. In the middle there are cats, so the true cats, which are in the family Felidae. Above is an extinct group of saber-tooths that were some of the first ones to form in North America is where they first appeared, but also in the Old World. And then even when you go back 250 million years, this creature over here, that is something we call a Gorgonopsian, but you can see it has saber-tooth, or maybe you can, but I hope you can see it had a saber-tooth morphology, but was more of a reptile than it was a mammal. And then the one on the right, this is a marsupial saber-tooth that evolved in South America. So all of this shows you is an example of what Darwin would call convergence, when we see the evolution of similar forms in different species over and over, which is obviously signaling that this is a successful design, and it keeps reappearing. So they are not freaks, they were successful. Yes. Right. Okay, so where do they fall in the carnivore? The carnivores are put in an order called carnivora. You know, we biologists have this hierarchy. So we have an order called carnivora, and within it, there are two major groups, the dog-like ones and the cat-like ones, caniforms and feliforms. And the saber-tooths, of course, are in the feliforms, and the dog-like ones include everything, including, which is sometimes surprising to people, walruses and seals and sea lions are also more closely related to dogs than they are to cats. And another interesting one is the hyena here, which most people would think that must be more closely related to dogs, but it is not. It is actually much more closely related to cats. Yeah. So now let's go look closer in the feliforms, where the saber-tooths form and show up, and they show up in two families, which I've already talked about a little bit, the cat family, which we still have, the Felidae, and then there's this extinct family called the Nimrabids. So this is just to show you a little bit more. So here's the Nimrabids, which are the earliest ones, and there are two different groups in there, called Nimrabids and Barbarophilids. And then the true cats, what's interesting about them is that they produce both saber-toothed species like Smilodon, the one that's on the counter here, and then they produce cheetahs and lions and leopards and all the cats that we have today. And those have more conical shaped canines, so cone-shaped rather than knife-shaped. And we go further, but if we look into these saber-tooths, we see that there are, well, here's showing the conical tooth and the long, flat canines, so they're very flat from side to side, knife-like. And if we look within the saber-tooths themselves, we find paleontologists or whatever biologists, we've even split them yet again. We see two different forms that repeatedly appear. One's called scimitar tooth, the other's called dirk tooth, and you can see the scimitar has a relatively short blade, but it's longer, broad, anterior, posteriorly, and it'll be flattened like a knife. And then the dirk tooth is like our friend the Smilodon, has an extremely long, flattened blade. So these are two different cat types of saber-tooths that had somewhat different killing methods, no doubt, which I may mention. Okay, so I'm going to do a little physics. Some people will go, oh no, not physics. We're going to talk about the difference in the skull shapes between a modern cat. This is a clouded leopard, which is a living a cat that has the longest canines, relatively speaking, relative to its skull size of any of the modern cats, across from a Smilodon, which is like the one on the counter here. And you can see that they look different in a variety of ways. Their skull shape is different, their jaw shape is different, and of course they have huge upper canines. They also have in the saber-tooth, we see much larger incisors that are placed far in front of or not far, but in front of the canines, rather than closely aligned. And that probably assisted them in feeding on the animals they already killed, because they probably used their incisors to pull food off. And so we've got, yes. Next thing that's different, this is where we're going to get into the physics a little bit. See, this is the jawbone. It comes up behind this thing we call the zygomatic arch, and then that's the whole jaw. And you have this large process here, and it's called the coronoid process. On the saber-tooth, that same process is this little dinky thing, and you can maybe, in the front, if we're all anyway, see that it's quite small. So why do they do that? We're going to get into that. So that's one big difference. And the other difference that you can't really see in these slides, but they also, the saber-tooths have an enlarged area back here behind their jaw joint, right below the back of their skull, would be under here, that actually has muscles attached to it that pull the head down. Rather than just pulling the jaw up, they can pull the head down. And modern cats can do that, but they don't use that when they're biting very much. They just lift their lower jaw. But for these guys, pulling the head down became more important, became more important than in the regular cats. And the other thing is they have different skull profiles, meaning this is very rounded, and this one is kind of uplifted, and especially, maybe next slide will show this. Oh, no, this comes up later. Yeah, it's also the angle of this relative to the jawline is quite different. And these are all modifications that had to be made in order to work with those canines. So that's what we're going to get into now. The problem with being something like Smilodon is how do you open your jaws wide enough to clear a space between those upper canines and the lower canines so you can bite something? Difficult. So if we look at this diagram, so here's mountain lions, such as we now know are native to San Juan Island. As of last week, did you all see that? There's perhaps mountain lion on San Juan. That's a mountain lion. This is an early Nimrabbit, right? These are both Nimrabbits, an earlier one and a later one. All of these are drawn with the jaws open 65 degrees. And you can see that with 65 degrees, which is probably more than this cat would usually do, it has quite a large gape. But for these guys, even at 65 degrees, yeah, they're still, they're not opening as wide as that, or they can't take in as large things. But there is a clearance there. So the problem with opening your jaw wide is And it has to do with the muscles that are attaching to the jaw, that bone, on that coronoid process I mentioned here. So it's a big lever for this that pulls the jaw closed. And when you have a little one, you lose leverage. And there's another problem, is that if you open your mouth this wide, you're stretching the muscles that attach, which is called temporalis muscle. And muscles, when they're stretched, it's not like a rubber band that they get taut and taut and taut and spring back better. If you stretch beyond 1.2 times their length, they cannot contract very well at all. Okay, so that's an issue, and that's partly why. So let's see how this relates. So let's look at this temporalis muscle thing. So here's on a normal cat, like the cloud leopard. This is where the temporalis muscle sits, and it's going to insert on that coronoid process of the lower jaw. And when the jaw opens, so there's the muscle fiber. We'll just take that as a fiber. There's the center of rotation, the jaw joint, where the jaw is going to move. And so when this jaw starts to swing open, this little hook-like coronoid process is going to move around on this arc, right? And it's going to pull the muscle as the jaw opens and stretch the muscle as it opens. So it's a problem. If you have to open your mouth really wide, you're going to overstretch the muscle, and then you won't be able to close it very well again. So how did Smilodon solve this problem? Well, let's look at this one for it. So here's the mountain line, the jaw back to 65 degrees, and the muscles stretched to 2 times its length, so it would not have much force to pull the mouth closed. And then early Nimrabbit, it's only to 1.3 times, because they've made this reduced coronoid process, which now makes the distance between that insertion and the jaw joint much less, so it's moving on a smaller circle of that. So the muscles only stretch to 1.3, and on a later Nimrabbit, only 1.2, very small coronoid process. So that's why they reduce that coronoid process, which seems like a stupid thing to do because it's going to reduce leverage, but it's the only way to do it in order to still have the temporalis muscle be able to pull the jaws shut. But, as I said, it causes a leverage problem. And this is a leopard, and this is a Smilodon jaw. And here's how huge this coronoid process is. If you think of it as a lever, with this is the center of rotation, this is the in lever, and the out lever is the length of the jaw. So as this jaw is closing on something here that it's biting, that force is going to try to push the jaw down. This has to pull the jaw up. So the ratio of the in lever to the out lever is critical, and that's 1 to 3, which is pretty good in the leopard. But in Smilodon, because it's got this dinky thing, it's 1 to 6. So that, when people looked at that, or when we look at that, we say, well, Smilodon had weak jaws. How did this work? And we know it worked because they existed. But they did have an added thing that we don't see in leopards, which I mentioned before. So Smilodon is a low leverage system. There's a lion, which is a high leverage system jaw. What brings me back to those the muscles I said insert on the bottom of the skull and pull the jaw down. So when they closed their jaws, they lifted their lower jaw and they pulled their head down at the same time. Yeah, so kind of like this. Pull it down. Right. So that's how they solved. But people still debate and say, well, Smilodon had weak jaw muscles, and it's hard to know whether they did or they didn't, but they were successful. So, whoops. They were successful, so they were capable of surviving. They had enough that worked. Okay, so I mentioned how this face is rotated upwards, the difference in head shape here, and this rotation. So if we look at the sort of a line that defines the base of the skull versus a line that defines the upper tooth row angle, quite different. Smilodon, again, this is to create a larger gape that lifts its top part of its skull up, and that helps with creating the gape that it needs in order to use these big canines. And one of the interesting things, way of looking at this, so that how did a cat or something that looked basically like this evolve this shape? And this is where the fossil record is wonderful. So we can do something that's called geometric morphometrics, and you don't have to know much about it. Just this is a normal skull, and the scientist here, or whoever, has put dots here on landmarks, such as behind the last tooth, or at a certain suture, or another certain suture, things like that. So there are landmarks that are on all skulls. And then a suture is like where two bones come together. so, yeah, where your two bones on your skull meet. So in this case, and then you have your template of a normal skull, and you plot those same points on a saber-toothed skull, and then you lay a grid that you match to here, and you see how the grid is deformed. And it shows you how the shape changes over. You can use it, they're called deformation grids. You can use it to look at shape change over time if you have a sequence of skulls through the fossil record. So here you see, for a group of saber-tooths, starting with 9 million years ago, fairly normal cat-like skull. And then 3 million years, as the canine gets longer and longer, the skull deforms more and more. If you just focus on, I meant to mention, these 2 points, 3 and 4 here, which are here and here. Notice how far apart they are there. They're squeezing together, squeezing, as that snout raises up over time. So it's a really nice technique to document this change in skull shape over time, and you can do it for different groups. So that was one family of saber-tooths. That's the nimravids over there. And again, you see this pinching together at number 3 and 4, as that snout has to raise up to handle these large canines. So here's evolution solving the problem over and over again the same way, convergent. Nice. Okay, now the fun stuff. That's all. No more physics. All right. So here's a smilodon, massively built big cats, big bones, really long, muscular neck, powerful forelimbs, claws that can retract and protract like a typical kitty cat, and then short backs and tails. Combined with this set of teeth, which is relatively few teeth, but they're just purely designed for killing and slicing. Nothing for grinding up fruits or nuts or anything, nothing looks like that. This is a dentition that screams carnivory, and a skull that I've said is built to maximize gait while maintaining bite force. So, when we want to think about what they ate, somebody already mentioned this, like prey size, as we know from studies of living animals, then this is a simple graph kind of thing. It's as prey size goes up, predator body size goes up. The larger predators take larger prey, which makes sense. So bobcats, lynxes take mice, and lions take wildebeest, animals that are larger than themselves, which is unusual to take something large. We know that from the tar pits and other places that this is the kind of animal that Smilodon ate. So horses and camels and bison and mastodons and mammoths. And why is this and yeah, I think I was comparing the slicing teeth with the, tooth shape is going to be helpful in figuring out how these things kill. But here's Smilodon with these knife-like flattened from side to side, and then African lion, it's actually a conical shaped tooth. You can't really see that from the front. So, to understand how they kill, so Smilodon has these flat, knife-like teeth, and modern big cats like lions have conical shaped canine teeth. Well, it turns out we can learn something from looking at modern big cats and dogs, like wolves and jackals and African black dogs. And that will help us understand, helps me understand anyway, how Smilodon work. So felids, these are living cats, have these round, peg-like canines, so round in cross-section basically, as opposed to canids, which have more knife-like ones. So why would that be? Well, if we look at how lions kill things, this is what we see. Well, one thing about big cats is they often kill things on their own. A single lion takes down a single wildebeest. It doesn't happen with wolves very often, or wild ones. So they use a single strong killing bite They either do a complete chokehold, like this one. Now this is a wildebeest head, so he's just throttling it. Or, and this one, here's the eye of this buffalo, he's suffocating it. They cover the muzzle. They just hold the nose and the mouth shut, and the animal suffocates. They use a single strong bite to kill their prey, and they're able to do this because of their size and because they have jaws, paws, and claws. So cats have the ability to do this with their forelimbs. Dogs can barely do that. They are basically fore and aft. Cats can rotate and grab, and then they have these very large paws with large claws. So all that helps them hold the animal where they need it for a single killing bite, which is what they usually do. On the other hand, look at these guys. These are one of my favorite species of all time, the African wild dogs. They live in groups. They hunt in groups. They have to hunt in groups. They're like the only canid that's, as we call it, an obligate social animal. You never see a single wild dog living, or even a pair, on their own. They're always in groups because they're pretty lightweight, and in order to get what they want, they have to work in groups. So they come up and they bite at the hindquarters, and they do a bite that's like this, right? Bite and pull back, bite and pull back. And for that, it's better to have a knife-shaped tooth. So cats, felids have canine teeth that are built to resist loads coming from all directions. You have to worry about breaking your canines. So you don't want them to break. You have a round one. It doesn't matter if the animal thrashes this way or that way. That canine is going to be able to withstand that load. Canids have specialized their canines just for fore and aft loads, in and out, in and out. And that's what that shows. Okay, so what does that tell us about saber-tooths? Are they more like this? Are they more like this? They're more shaped like a canine tooth. So saber-tooths probably use multiple slashing bites to kill their prey, because that's what would work. And this is the bite that is, we usually think of them doing, where they would have their mouth wide open, hooking in those lower canines, and then driving these upper canines through, meeting the lower jaw, and then perhaps pulling backwards. Right? So so the head depressing musculature, you can see the magic coming into action here as it pulls the thing backwards. So it allowed them to make one big bite, at least, and then maybe another one. So where would you want to place that bite? Would you want to try the back of the neck? Would you want to try the thorax, the chest of this giant ground slug? Or would you think maybe the abdomen would be better? Since you could maybe avoid your teeth contacting bone? Because one thing with those narrow knife-like canines, you don't want them to suddenly hit bone and snap. And we do know that they did break. You can go to the tar pits and see canines that, some of these skulls have canines still in them, and the canine teeth, and they're one's gone or blunt, it's half gone, but it's warm. So the animal lived for some time afterwards, despite losing it. But that's not a good idea. You want to keep the canine. Or you go for the throat. You guys want to take the vote? So given the knife-like shape of their canines and their vulnerability to fracture, they probably tried to avoid bone. So yeah, the neck back here is probably not a great idea because there's a bunch of vertebrae right under there. And the thorax is this gigantic rib cage, so you probably don't want to go there. The abdomen, there's a little space here, right? So, but that's a space that kind of depends on where that leg is, how big it is, and whether you could get in there. And we've got these ribs that you don't want to get in here either. So, given that, what's the best target? Did I leave your witnesses to say? Throat, that's right. That's the throat. Yeah, right there. Because here, all this stuff here, there's a vertebrae back here. This is all soft tissue. And it's not just any soft tissue. You know what's in there, right? There's like your windpipe, yeah, and there's carotid arteries and jugular veins. It's all there. It's all there. So that's the place to go for a quick kill. And if you look, this is, I didn't give credit, but a lot of the artwork here by this wonderful guy, Mauricio Antón, who's in Spain. But he's doing an illustration here showing the saber-tooth taking down a horse, applying the bite, and here's an up close. So here comes the canines in around this cross-section of this poor horse's neck, and what you can see is that there are all these things like, I thought I had it written, yeah, the trachea, your windpipe, carotid arteries, jugular veins. So they could do one bite, bang, and then it would probably, the animal would bleed to death. It might take two. But that was probably the way they did it. Okay, so why evolve saber-tooth teeth? Because I think, I get asked this a lot, because I think it allows you, we already talked about that, to take larger prey. It probably allows you to kill something fast, and that's a good thing, because that minimizes the chance of you being injured by whatever it is you're killing. And it probably, having those saber teeth and killing quickly, allows you to better defend your kills from other carnivores and enhances your ability to steal kills from others. So that's my notion that if something like a saber-tooth walked up to you and just went, ha, you'd probably get out of the room, right? And I think dire wolves probably backed off from saber-tooths as well as bred wolves and mountain lions and anybody else. They were not to be messed with. All right, which brings us to the question. Another thing that is good for defending a kill is working in groups. So the question is, was Smilodon social? And it's really hard with the fossil record to figure out if an animal was social or not, unless you happen to find, you know, some kind of mass death site where it's a family group or something larger than you could make that inference. So it is kind of tricky. In this illustration, they have them as social. This is from the target. But yeah, were they social or solitary? So I wondered about this, and I had a colleague, Chris Carbone. We were trying to figure out a way to get at this. And the simple expectation for Smilodon would be, no, they were not social. And I say that just because in modern big cats, none of them are social except for the lion. It's uncommon. Tigers aren't really social. Leopards aren't social. None of the big other mountain lions aren't social. So why would the saber, you know, it seems like cats don't do it, and they can kill on their own, so they don't need this pack kind of thing. The lions do it, but anyway, the default answer would be no, they're not social. So Chris and I were trying to figure out how to get at this, and we had a kind of interesting idea or observation of another study that was done in Africa on living carnivores, what I'll get to in a minute, and we're comparing it to the Rancho La Brea tar seeps. So for those of you that haven't been to LA or don't know what these are, here's Wilshire Boulevard today, and in the past, and the tar seeps are right around here somewhere, 15,000 years ago, it was a very different place. And the way it works is that you have layers deep below, underground, that are tar, that are from millions of years ago of organisms dying and the carbon building up, et cetera, and that's tapped for oil, for gas, and everything else. But it will come to, it's lighter than water, so it will rise if it finds a pathway to the surface. And in LA, there's all this tectonics that goes on, you know. So the tar can seep from these layers up to the surface. So you get these things called tar seeps. And in the downtown here, where there's an area where there are lots of them, and it'll seep there for a little while, and that one will close off, and another one would come up. And these are very interesting fossil collectors, in fact, 15,000 years ago. And we'll get to that. Yeah, so what would happen is the tar would come to the surface, whoops, sorry. And you have this sticky asphalt on the top, and it probably got covered up with leaves and maybe water. And an unsuspecting animal would walk out onto it. This happens to be a mammoth, I think, that walked out and got stuck. And we know that. We have their bones at the tar pit. And struggled and probably made noise, et cetera, and died. And it attracted predators. You see a saber-tooth here, you see a dire wolf, and you see a lot of vultures, which were also very common at the tar pit. So it is a predator trap and a predator attraction event when something would die. All right, so that's what we say. Rancho La Brea was a predator trap. It's very unusual as a fossil deposit because there are about 9 big carnivores for every herbivore that died there. So that's the opposite of what you see on the landscape, right? We should have plenty of zebra and a few lions. This is reverse. So it is a predator attraction. It was, and it was a predator trap. All right, so what is that? So this study came up. These people who studied living carnivores in Africa were using a method of censusing. They wanted to count the number of spotted hyenas and lions and whatever in an area. And so they drove out into the Serengeti, or it was Kruger's one of the national parks, and put a speaker on the top of the roof of the van, and they played the sound of a wildebeest dying, or the sound of hyenas on a carcass. Hyenas make all kinds of noise when they're killed, and lions sometimes do too. They played those kinds of sounds, and then they sat and waited and saw who's coming. And they wanted, they were trying to see if they could get all the hyenas in an area to come, so they knew that this would be a good way to count the number of hyenas in the area. That's not why Chris and I were interested in this. We're interested in who comes to such a thing, right? So, and here you see lions and hyenas fighting over here, and here we have our other friends from Tarpon. Well, the interesting thing is that when you look at who came to the sounds in Africa, the modern study, social carnivore species were much more likely to show up. 85% of the animals that showed up were lions, hyenas, or jackals. Large and small solitary species made up less than 1% of responders. So things like leopards never came, and cheetahs actually moved away. Why do you think? Does anybody want to say why they think this is the case, that only social ones would come, or were?
Because if you were just you alone, you couldn't protect yourself.
That's right. That's exactly right. Why do social species predominate these events? Because they're pretty dangerous events. Because if you hear that noise, that the hyenas are good. If you're a lion, hyenas are probably going to get there. Or if you're a hyena, you think, oh God, when the lions are there. So I'm not going to walk up to that alone. And especially, it's just too risky to go alone. And these are the other ones that showed up. They were pissed off, whereas they were going to drive off the lions and hyenas. They showed up, the Maasai showed up, 2% of the attendees were Maasai, kind of saying, hey.
Are there bones in the tar? People bones?
No, not until very recently. There is one Indian Native American
Tourist.
female. No. Maybe, no. Yeah, we're going to make a movie about that, yeah. Okay, so let's look at Rancho La Brea now from that point of view. So here's this pie chart again. So all of this is carnivores, and those are the herbivores. And here are the numbers at the tar pits. The dire wolf and Smilodon are definitely dominant. Over 1,000 of those and 1,700 dire wolves. And then we also have the lion and short-faced bear, but not as much. And the coyote, small coyote, 255. So the main players are the saber-toothed cat and the dire wolf. And here's my pie chart for Kruger National Park. That's in South Africa that I showed you before. So 85% social, and then the rest of this is like small social and then solitaries. And what happens when we look at La Brea, if we assume that saber-tooths were solitary, then that means this is just the dire wolves over here. This is the saber-tooths, and then we have the small socials. So it doesn't look very similar to that. But if we make the other assumption that they are social, then we got almost a perfect match in terms of the percentage of individuals that are there. So it's kind of a weird, it's not your typical scientific argument here, but it is, it's consistent. This is consistent with them being social cats. And that's about the best evidence we have. So, yeah. So I think, at least at Rancho La Brea, they were social. It is true that lions even aren't always social. So you can sometimes, they can exist as pairs, but of course nowadays there are relatively few lions, so it's hard to extrapolate that. All right, and everybody wants to know this. This is the hardest thing to answer. So I'm almost at the end here. Why did they go extinct? It's hard. That's a hard one to answer. But what I can say is that they went extinct about 12, let's just say in North America. Well, that is where the last saber-toothed existed. We're in North America. And Smilodon. And went extinct around 12,000 years ago. Around the same time, after it coincides with, follows the arrival of humans on the continent of North America, and a notable increase in fire frequency and also aridity. So there was a climate change situation going on around 12,000 years ago that had to do probably not with the humans, was just increasing aridity and dryness. But those kinds of events had happened before over the last many millions of years and thousands, hundreds of thousands of years, and these guys lived through that. So the added component here is the humans, and it does seem that fire was, they were instigating fire, using fire to drive animals or whatever. And so that is probably what happened, because we lost them, and that there was, oh yes, and another interesting thing is it wasn't just these things that were lost, of course. It was their prey. That's what the humans were killing their prey, and I think they drove the biomass of the bison, and there were many species of bison, not just the one we had before. The bunch of bison, camels, horses, mastodons, and mammoths. They drove their populations so low that this affected these guys and the all big. Yeah. Is there a question? Yeah.
Yeah, was that, so you said that they were on these 4 or 5 other continents.
Yeah.
Does that logic hold up with the human populations that were present over there before?
It's interesting. So Africa, the saber-toothed went extinct earlier, but there were people there earlier.
Sure.
And then also in the old world, they went extinct earlier. So so it kind of is consistent with that it is human influence. And I do think another interesting answer to whether, why all these, so they went extinct. We lost the saber-tooth, we lost the dire wolf, we lost the giant short-faced bear, and I'm leaving one other. And who else am I going on there? There's one other big predator we lost. Yeah. Yeah, I think I said that. But the lion. We had a lion here too. We had an American lion. So we had an American lion, a saber-toothed, giant short-faced bear, dire wolf. All of those would have been predators of very large prey. And so that seems that we took that resource really crashed around 12,000 years ago. And because it's also interesting, these guys all went extinct too. There were like 7, 10 species of vultures at the tar pits we know of. It looked more like Africa where you see all the different types of vultures. And those guys don't care what they eat. It could be small, it could be big. They just need meat, right? So their loss, their disappearance makes me think that the biomass on the landscape just went way down. Yeah. So combination of fire and climate change.
So how do we explain that the saber-tooth went extinct in Africa earlier, but there's still obviously big cats in Africa?
Right.
So how should we reconcile that? So the saber-tooth went extinct in North America, it also went extinct in Africa, but then you have these other big cats that survived. What would be the differentiator between that?
Yeah, good question. But I think, and nobody's really done this, maybe I'll work on it, I don't know. I think that these cats the saber-tooths were more specialized in terms of not being able to switch prey. So like, yeah, you could say, well, why didn't they just switch to deer or to antelope or something? It was Africa. And I think they're too bulky, they couldn't move that fast. So we don't really understand, like the dire wolf went extinct, but the gray wolf lived. Why? Those two species are very similar in shape and size. Dire wolf lived there. But why? Why didn't the dire wolf switch to moose and deer when the gray wolves did? That's still a puzzle.
The next generation will pick up that question.
Yeah, that's right.
What was that?
I guess I just got why are there examples of large predators that have gotten smaller just to match their prey size? And if maybe not, but if so, why didn't they track to that?
Yeah, they couldn't, and they didn't do that. There aren't very many good examples of animals getting smaller. in being able to do. I mean, theoretically, you would think that would be possible, but they kind of, you know, they've become large and they're muscular all over and their bones are, it's a big transition backwards, so it just doesn't seem to happen. You know. I'm trying to think if there must be one example.
Was there a prey species that they went after sloths or whatever that was getting larger at the same time they were, that would explain why their teeth were getting bigger?
Yeah, people tried to look at that over the, not so much just with the tar pits, but the earlier saber-toothed and in the old world. And I don't think they've been able to, they've made some sorts of correlations, but it's not clear. It's not clear. Yeah. We don't have a nice matching of both of those things. Yeah. Yeah?
It's been a long time since I've been at La Brea, but I can't remember how it is you figured out how to get the bones and other mass out of the tar pits.
How they get it? They extract them and then they wash them. And in the original old days, when they first started excavating in the 20s and 30s, they just rinsed them in gasoline. There are pictures of these guys standing with these troughs, gasoline, and they're washing it. No masks, of course, none of that. No gloves, none of that. So now they use a solvent that's nicer, a little healthier, and they have hoods when they do it. But whatever. But yeah, you just have to clean it off. You can dig in it, but they make like a wooden platform above the tar so that they're not in it, right? yeah. They still get pretty messy though.
We're still digging at possible.
Yeah, they have one site there, and then when they built the new art museum next door, they found a whole bunch more stuff. That's all in boxes. They didn't even take it all. They took them out in like the boxes that you see adult trees being transported about. Yeah, I think I can't remember the name, whether it was 50 of those boxes, and those are to be cleaned up at some point, although with funding the way it's going, not soon. Yeah.
What's the length of the fossil record at La Brea? Do you see this change in the tooth length?
No, it's very recent. La Brea is only, it may be a couple 100,000, but I don't even think the most productive pits are less than 70,000 years old. Yeah, that's fairly recent, very recent. Yeah, and it's interesting because it actually crosses the extinction zone. So the coyotes make it through, and so some people are comparing the coyotes, their morphology, their size and stuff, before and after the extinction and things like that. There's work on that right now that people are doing. Okay, anything else?
I was just curious if the tar pits leave anything intact of the animal's fur, so you can see what it looks like, or is it all gone?
It's all gone, and even, so if you go to the tar pits outside, there are these sometimes chain link fence cages around an area that's maybe about the size of what you're sitting on here to keep, and that's where a new seep has come up. And they've had, I remember hearing this, that a dog jumped over the fence and was in it, and they had to rescue this dog from there. And they did rescue the dog. The dog was fine, but it lost all its fur. Its fur.
Oh.
Yeah. That's what they told me.
Crazy.
Yeah.
Thank you.
Oh, good. Thank you for coming.